Navigating the modern healthcare system brings an immense emotional toll, which is immediately compounded by the bureaucratic weight of opaque medical billing. The core systemic failure driving this stress is information asymmetry. We have massive insurers with vast data access on one side and individual policyholders left entirely in the dark on the other. Insurers rely on complex rules engines built entirely out of specific corporate jargon. Terms like copays, sublimits, and domiciliary coverage act as legal mechanisms to mask significant out-of-pocket expenses. Looking at this visual, we see the immediate result of these dense policy documents. Patients are blind to their actual financial liability right up until they receive an inflated bill after their medical procedure. To solve this, our engineering objective was clear. We needed to build a continuous, autonomous expert system that translates this corporate jargon and proactively flags financial traps before the patient ever commits to surgery. Resolving this data asymmetry requires an architectural intervention designed to prevent catastrophic medical bankruptcy, rather than a superficial user experience adjustment. Parsing this specific type of medical data is notoriously difficult. Historically, standard AI classification models have struggled to manage it. Standard decision trees break down against unstructured healthcare data. Monolithic LLMs carry unacceptable risks of hallucinating coverage rules, which is disqualifying in regulated insurance domains. The solution is agentic workflows, splitting logic into specialized agents, strictly constrained by deterministic Python tool calling in a sequential flow. Deploying probabilistic AI into a high-liability, regulated environment works only when that AI is explicitly wrapped within strict deterministic code boundaries. To build these precise deterministic boundaries, we utilize the Google Agent Development Kit, or ADK 2.0. This network visualization maps the core of our system, a stateful 9-node graph workflow, relying on the Gemini 3.5 Flash model for natural language reasoning. We establish our first distinct AI persona right at the origin, the extraction agent. We explicitly forbid this node from making decisions. Its isolated function is to parse chaotic user input and format it into a strict, verifiable JSON schema. Once verified, this JSON payload is handed off to deterministic backend Python tools, which use the structured data to query external hospital databases. Downstream, we introduce our second AI persona, the risk analysis agent. This agent operates as an independent, isolated LLM auditor. It reads the verified JSON against the retrieved policy rules with a single objective: hunt for hidden financial traps. By physically isolating these AI personas within the graph, we prevent the cross-contamination of logic. The natural language engine is architecturally blocked from inventing or hallucinating policy rules. We can prove these precise safety constraints by running a real-world, high-stakes medical scenario directly through the newly built system. A user inputs a specific request. They want an appendix operation at Max Hospital. The cost is $3,000, and their policy number is POL 123. The initial data flow works. The extraction agent parses the intent, and the Python tools verify that the hospital is in network. But the risk analysis agent flags a significant trap. Policy POL 123 actually enforces a hidden 10% copayment and a strict $150 room rent limit. Because we engineered a zero-trust response, the Python decision node refuses to approve this flagged claim. As shown on the left side of this split screen, it hits a red node and abruptly freezes execution. This is where asynchronous state management becomes necessary. We utilize a human-in-the-loop gate to handle edge cases safely. The ADK graph immediately writes the paused session state to an SQLite database, securing the data. On the right side, a custom glass morphism dashboard instantly populates, presenting the specific policy traps to a human claims adjuster. The adjuster executes a manual override by clicking Processing. The dashboard transmits a REST API payload back across our stack to the ADK backend. The red node turns green, and the workflow flows continuously to a complete state. Zero Trust AI utilizes human experts for complex edge cases, algorithmically pausing execution at the exact moment of catastrophic financial risk. Prototyping this complex graph architecture requires an agile engineering methodology. We utilized vibe coding, collaborating side by side with an agentic coding assistant to rapidly construct the framework. The stack relies on Google ADK, Gemini 3.5 Flash for instruction reasoning, and Fast API to bridge the interface. Before trusting this stack with actual patient data, we instituted a rigorous testing protocol to mathematically prove the system's safety. Using the Google Agents CLI, we engineered a custom LLM as a judge evaluation suite to test the model against edge cases. This performance graph illustrates the empirical results. Across all core trap detection scenarios, the agent achieved a score of 5.0 out of 5 for both correctness and plain language translation. That score directly addresses our initial domain problem. By applying deterministic testing protocols, we can quantitatively validate the safety and accuracy of probabilistic language models. The final engineering step was transitioning this validated local prototype into a scalable production environment. The system has been fully deployed and tested on Google Cloud's Vertex AI agent engine. Combining the immense reasoning power of Gemini with the strict stateful routing of ADK resolves the tension of utilizing AI in high-liability sectors. This specific agentic architecture systematically dismantles the opaque and hostile rules engines deployed by corporate insurance. Utilizing human-in-the-loop agentic AI for medical billing rebalances power from the insurer's black box back to the patient.